Okay, so we're looking at question number 1. This we're saying helium gas is flowing steadily through the pipe shown above. The diameter of the pipe at the left end is 2 times 10 to the negative second meters, and at the right is 1 times 10 to the negative second meters. The flow is slow enough that the density of the gas remains essentially constant. The volume flow rate is 2 times 10 to the negative third meters cubed per second. What is the speed of the gas in the left end of the pipe? So what I want you to do is try this one out on your own, then just kind of like pause the video while you're trying it, and then I'm going to solve it right now, but pause it, and then for me it'll be right now, but for you it'll be after you tried it, and then we can compare answers. Oops. Okay, so question number 1. So we're saying the diameter of the pipe at the left end. We know something about the diameter at the right end. And really quickly, this is helium gas, but it's a gas, so it's still a fluid, so everything that we're doing still applies. Everything that we've tried, everything that we've done, all of our equations, they still apply. Even though it feels a little bit weird to have gas in a pipe, it's completely normal, completely usual. It's what my brother does for a living. Yeah, so we want to know what's the speed at the left end. So if we're kind of looking at this, we know something about the dimensions on the left. We know dimensions on the right. We know something about the speed. We know the volume flow rate, so then we just want to know the speed. So the thing about volume flow rate that we know is we know that we have this quantity, this Q for volume flow rate. This doesn't show up on our equation sheet, but we know that the volume flow rate is equal to A1 times V1, and we know that that is constant throughout the pipe. So this is really our continuity equation, this conservation of mass, conservation of volume kind of equation. So we know that this volume flow rate, this volume per time, is the same as saying A1 V1. So we know the volume flow rate throughout this pipe. We know in the left end, we know in the right end, we know that it is conserved. It's the same throughout, as is 2 times 10 to the negative third. We want to know the speed in the left end of the pipe, and thankfully we know the diameter at the left end of the pipe. So if we're looking at this, we want to solve really for this V1. So we can say A1 times V1. So we don't directly know A1, but we have enough that we can solve for it. We know that the diameter at this first part, the left end, is 2 times 10 to the negative second, which means that the radius is half of that, so 1 times 10 to the negative second, which means that our area, because it's a circular pipe, is just going to be pi r squared. So area is equal to pi times 1 times 10 to the negative second squared. So we can plug in. We can say 2 times 10 to the negative third is equal to pi 1 times 10 to the negative second squared times V1, and then we are good to go. Okay, so when we plug this into our calculators, we get 0.002 divided by pi times 0.01 squared is V1, and then we can say V1 is equal to 20 divided by pi, or 6.366 meters per second. So either one is fine. All right, and that is our first one. So remember that our volume flow rate is constant, and that the volume flow rate, even though this is not on the equation sheet, is A1 times V1. One way that we can think about this is units. Our units for area is meters squared. Our units for velocity is meters per second. So our units for that is meters cubed per second, which is volume per time.